Hi guys, so we have finished a module. We finished module 1, or at least I've recorded all the lectures, I've delivered them all, and you've also received your assignment. There's no guarantee that you've watched all of those lectures, but by this point you certainly should have done. All of module 1 we've done. So we're starting a new module now, suitably entitled module 2, and we're going to have a look today at some things I'm going to give you an overview of this module. And as I already mentioned on Slack, this module presupposes a lot of knowledge on you guys from previous courses 200 and 202. So I'm going to talk about what we're doing in this module and the bits that I expect you to know, and then I'm going to deliver a couple of lectures tomorrow on the things that I think you should know but you might need a bit of revision on. And that's not a criticism of you guys, this is just I remember being an undergraduate student. I can remember studying really hard for exams in things that I think sort of left my brain. It was a temporary storage space until I did the exam and then it was gone. So some things you'll need a refresher on, and it's always good to have a refresher and just see another explanation of how we do things. So we'll do that over the next couple of days. And I'm going to talk more about what this module involves. So we're looking at module, let's bring this up. I haven't got my notes up. Notes up on the screen. Okay, so module 2, this is obviously Aerostructures. We're looking at statically indeterminate structures, and we are specifically looking at truss frame structures, which are super interesting. Let's firstly speak about what we did in module 1, so the things that you should know. So we introduced some new concepts for you guys, things that a few of you may have already known or already heard of before, but we're just going to remember the key concepts that we've picked up. So shear center is what we introduced, and we defined this as the points in a two-dimensional section which if we apply a point shear force, then we only get bending, no torsion. It's not a very good description that I've given there, but I did a whole video on what shear center is. So if you're still not certain on that, make sure you go back and watch that video. We introduced this idea of shear flow. So we had QS, which is got the units of newtons per meter, and it's the way that we consider those internal shear forces propagated through structures. And we came up with the all-important equation for us to determine shear flow is equal to minus, if we've only got a vertical force, for example, Vy on Ixx, and then for a thin wall structure, we have the thickness, which can be a function of S, the Y displacement, which can be a function of S, ds. So the thickness is the thickness of the wall that we're looking at. Ys is the displacement from the centroid of the wall, which is a function of S, to the centroid of the object. So we use this expression a lot to develop the shear flow for open sections. So this would be the shear flow for an open section. Sorry, my screen's lagging for me to look at. I can deal with it, but it's why I look a little bit confused. So this would be the shear flow for an open section. An open section with only Vy. If I had a Vx, I'd have a Vx on Iyy, Ts, and then I'd have Xs here, ds. Which would be another set of terms to add. And also, all of the sections that we looked at were symmetric. So as long as we've got a single axis of symmetry, we can use these expressions. If we don't have the single axis of symmetry, there's complicated other terms that are introduced due to the products of inertia. We're not going to bother looking at those. We're not going to look at those because they're just too complex and they are effectively more of the same. So this was right for an open section. And then we said for a closed section, we have the shear flow is equal to some offsets plus the basic shear flow distribution. So this would be the open or basic. And because it's equal to the open shear flow distribution, it's equal to this thing up here. Okay, the same. And then this is an offset to be determined. Okay, so we have these two definitions of shear flow distributions. We use them for closed sections up here. We said that if we have a closed section, we can use this to determine the shear center. And we said the moment due to the applied shear force is equal to the moment due to the shear flow, which is where we integrate the shear flow to turn it into a force, multiply it by a moment arm. This was only if Vy is at the shear center, or if we were doing a problem flip through 90 degrees, it would be if Vx was applied at the shear center. For the open sections, sorry, for the closed sections, these ones down here, then Mv is equal to Mq wherever we apply Vy or wherever we apply Vx. So I said that expression there, Mv is equal to Mq, is independent of the loading position. So we can use this to determine Q0 if we know where we're loading. So for example, when we had that box example and we have a Vy known loading position, we can then determine Q0 using that. If, on the other hand, we don't know where we're loading and we're trying to determine the shear center, if we want to determine the shear center, we would define the distance as being some arbitrary, we'll give it a letter, we'll say it's E, we'll say it's zeta, we'll say it's beta, whatever, and then we will use the other expression. We have Q0 is equal to minus closed contour integral of Qs divided by the shear modulus thickness ds divided by the same, which is just 1 over dt. So these were these closed contour integrals, and once we get Q0, we can then use this expression to determine where this is true, and this would then enable us to determine what where the shear center is. So I've tried to sort of talk through the theory of shear center determination, shear flow, without going through an example. This is a real top level discussion, and hopefully you guys have gone through the examples, you've gone through your homework. I know some people have already finished the homework, which is amazing, really good, okay? So if you're having problems with this and some of the theory, drop me a message and I can try and record some new things. Okay, so I sort of talked over the bit that I was going to say. I said that we were able to determine the shear center of thin wall structures, and we looked at closed and open sections. Bingo. And giving you this homework, there's a due date on that. I think it's next weekend now, or this weekend, the one that's about to come. So go through this, ask questions. People have been asking them on Slack already. People ask me questions sort of directly. I tend to reply, take a screenshot, wipe their name out and share it with the rest of you, because to me that's the equivalent of someone putting their hand up in an exam. So I want to be able to share anything I tell you, I should be able to share with you guys. Okay? So we are moving on to a new module now, module 2. Let's have a look at what this is going to involve. So we are looking at statically indeterminate structures. Okay, and we're very specifically looking at truss structures or truss frames. We look at truss frames now, that sort of sounds like one of those engineering things that we look at and we never use. But when we looked at actual real airframe structures, we saw that light aircraft and lots of real production aircraft have truss frames in them. They're a useful way of transferring loads using two force members. So these are incorporated in airframes. We do use them. They're not just something we can use an engineering diagram of and it's good for students. They are things that we use. But we're not using them just because they're used in airframes. We're going to use them because they're a really good way to do problems in class. They're a really good way to make problems that are amenable for students to solve. And importantly, they enable us to introduce some really cool new things, some really powerful new methods that I'm going to give you a good overview of today. These new methods we're looking at WorkEnergy Methods, and we're looking at the principle of virtual displacements. Okay? So this one here is really important. It's going to help us solve things. This one here is magical. So cool. Such a powerful bit of mathematics and physics. Such a great way of thinking about things. So let's just go through and think about, I'll talk about what these things mean. So WorkEnergy Methods. Let's go over here. Okay, so the units of work and the units of energy in the SI system are both joules. And one of the fundamental tenets that you will have learned in thermodynamics, hopefully you learned in high school in sort of physics, the fundamental tenet is that we can't get rid of energy. We can't create energy, we can't get rid of it, we can only convert it between its forms. And that's going to be really useful for us. Okay, we can think about the net quantity of work or energy within a closed system must stay the same. It must be equal to whatever it started with, and that's going to help us understand how to solve these problems. So you probably looked at some work energy methods in dynamics. You might have used them to determine, for example, the equations of motion of a system. And often they're really helpful because work and energy are numbers that we can determine often more independently of the geometry of a problem than we would when we have to, say, look at force balance. So that's why they're going to help us for these problems. And again, I'm going to go through all of the theory with you. I'm just going through the sort of top level. Here's what we're thinking about. So we're going to consider energy is just stored, or energy is the ability to do work, or we can think about it as stored work. Okay, so we can think about energy, and there's different sorts of energy we've dealt with already. We've got kinetic energy, chemical energy, potential energy. We've got thermal energy, which is really just molecular kinetic energy. But the ones that we're going to be looking about, we're going to consider stored work being stored in the form of strain energy. Okay, so internal strain energy. So consider energy being stored as internal strain energy. And then there's got to be a work that we're going to compare this to, and we're going to think about the external work that can be done on a system. So for work to be done, we need, from the definition from physics, we need a force, and we need a displacement along the line of axis of the force. And we're going to consider the external work done. Okay, so for example, we remember that work done is equal to force multiplied by displacement. And we're saying here that the force and the line and the displacement have to be defined along the same vector for this to be true. Okay, so these are useful for our purposes, because when we're looking at an elastic structure, we're going to think about forces applied to certain parts of the structure, and then how much the structure deforms in the line of axis of that force. And what that has to be equal to then is any internal strain energy that's stored due to that force being applied. Now, it might not sound like that's particularly useful in this sort of first instance, but what we're going to find that is really going to help us determine the displacements of structures, and specifically it's going to help us determine the displacement of truss frame structures. So if you've been using the sort of the force and extension methods that you've maybe got from 200 and 202, we'd resort to understanding where structures sort of disassemble, use a lot of complicated trigonometry to work out the new shape. The methods that we're going to introduce enable us to really quickly understand where a displacement occurs due to that sort of line of action. Now that's what we're using this for, so I'm going to go back up here. So work and energy methods we're going to be using primarily, fundamentally, singularly, to look at the displacement of structures when we apply forces. My camera's just gone. Let me unplug and plug it back in. Hopefully that'll work. Let's try that. I don't know what's going on with the camera. There we go. Okay, so we're looking at the displacement of structures. And this is the work energy method is going to fundamentally make this a lot easier than any of the theory that you've had before. With less hassle, we'll say. And the reason that I'm introducing this, the reason we're doing it for these sort of simplified truss structures, is because it's quite a different way of thinking about deformation and about structures than you maybe have already. We're going to call it a bit of a cognitive shift in the way that we're thinking about problems. Okay, and so for example, when you looked at this in dynamics, you could solve problems without directly invoking Newton's second law. Okay, and because Newton's second law's got a force and an acceleration, both of which are vectors that have a direction, then that is what can be problematic. When we're looking at work and energy, those can just be scalar constructs. Okay, so that's why we get rid of a lot of the geometry from the problem, and it's going to help us. So let's go back over here. I said here on work energy methods. This is all the stuff I said about them. So we're going to consider stored energy in a structure as elastic internal strain energy. So when we've got a structure and we deform it, we can think about that energy being stored within all of the internal extensions within a structure. So if parts of the structure are stretching, they are storing elastic strain energy. And we're going to think about that. That's going to be quite easy to work out. So we're going to make that equivalent to any applied forces and the displacement of the structure in the direction of those forces. So that's going to be our external work done. And that means that we're very easily going to be able to determine what those displacements are. Now this means that when we use this up here, we can use this to look at the displacements of structures with less hassle, as long as there is a force applied in the direction that we care about the displacement. So more often than not, we might want to determine what's the displacement in a direction that we don't know, or where we haven't got an applied force. And we're going to have to think, well, we've got to think of a new method of doing this. And the answer comes down to this methodology, the PVD, Principle of Virtual Displacements, that I've already sort of told you guys how excited I am to teach you. So with the Principle of Virtual Displacements, you know, by the time we get here, you guys are going to be old hands at WorkEnergy Methods. You guys are going to understand it in and out, and you'll just know, yeah, right. So internal strain energy has got to be equal to the external work done, and I'm golden. So as long as we've got a problem for which you have a force being applied at some part of it, you'll be able to solve those problems in your sleep. And what we're going to move on to, we'll say, how do we solve displacements of structures where we don't have forces being applied? And the answer is simple. We're going to just say, okay, we're going to apply a virtual force at that point of the structure. We'll make one up. So we'll invent a fictitious virtual force that we're going to apply to the structure. So we'll apply a virtual force, and then we're going to determine what are the virtual displacements. And once we've determined the virtual displacements, we'll actually then be able to do a little bit of mathematical wizardry to show when we apply those whenever there's a real force on the structure, as long as we apply a virtual force in the direction that we want to know the displacement, we can look at the effect of those actual real loads, which can be anywhere on the structure, and we can look at how much they cause the structure to deform wherever we've applied these virtual forces. And what we're going to show is actually these virtual forces we apply, these are just going to be placeholders. And these placeholders are carried along with the real forces, and they do virtual work. And so they're carried along with real deformations, which does virtual work. And if they do virtual work, we can then make that equivalent to external virtual work, which means we can then work out the deformation of the structure wherever we applied these forces here. Now this is a real top level. I'm not expecting you guys to understand everything here, but I want you to have this appreciation of what we're about to be looking at. And this is a roadmap of where we're going to go. So we need to look at truss frame structures, and we need to understand how we can apply deformations using WorkEnergy methods. And then we're going to say, let's make some stuff up. Let's make up some virtual displacements. Sorry, let's make up some virtual forces. We'll apply them. They're placeholders. They get carried along with any real deformations. And accordingly, they do virtual work, which must be equal to external virtual displacements. So it must be equal to external virtual work, which means we can get these displacements on the real structure. Okay, that is amazing. This concept is fantastic, and it is something that I've already been waxing lyrical about it. This is an amazing piece of mathematics, and it's such a powerful way to look at structures, because what we're going to find is that we can then determine displacements of structures in any direction due to any forces applied that are independent of, say, the geometry of the problem. And what we're going to find when we do these a lot, we're going to have to sort of solve problems several times over, because we're going to have systems of real forces applied to structures, and then we're going to have some virtual forces. And if we're using the force method, which I know you all learn in 202, then we're going to have to apply another set of forces as well. So we're going to need to do a lot of these things over and over and over again. So we're going to be looking at some theory you guys should remember from 202 to go through that. Okay, so we're going to look at a few things. We're looking at what 2D truss frames are, and I'm going to give a bit of this now, and then, after I've gone through this bit, we need to remember what static determinacy and what indeterminacy is for a structure. You need to be good at doing 2D free body diagrams. You need to be hot on the method of joints, and you need to remember the force method. So what I'm going to go through is, we're going to do these briefly, not briefly, we're going to go through this now, a reminder of how we go through these things. I'm then going to do a separate video on these. I'm probably going to record that tomorrow and release it. This is really just revision, okay? And part of the reason for revision is because, as I've said, I remember as an undergraduate, you need to learn things 3 or 4 times before you really understand them. But also, I probably use different nomenclature to you guys doing it. And from speaking to some of you, I don't like some of the language that's been used in talking about the method of joints. I don't like, and you see it in some of the books like Megson, I don't like speaking about cutting members and then looking at things, because you're not cutting anything. We're going to think about the physics in the problem. We're thinking about how we're looking at determining equilibrium at a joint. That's what this is, the method of joints. Pick a joint, what forces must be present to maintain equilibrium. It's just geometry. We're going to go through that. And then the force method, we're going to cover this in a bit more detail, because this is one that's really poorly understood, I remember, by students. So we're going to cover this probably on Wednesday. And we're going to go through these examples. So these first bits, so these are going to come out tomorrow. This is going to be out on Wednesday, just as asynchronous videos. And everything we're doing here, we're not yet going to look at work energy methods, okay? Because we're going to find that we can sort of deal without work energy methods for really simple structures. But as soon as we've got a bit of complexity, we will find the usefulness of invoking work energy methods. And then probably next week, maybe towards the end of the week, depends when I get done with this stuff, we'll start to introduce work energy methods. But we'll quickly discover why we need them. Okay. So let's go through this yellow bit. Let's do a little bit of revision of what 2D truss frames are. And I'll touch a little bit upon the method of joints and the force method in this part as well, but I'm not going to go heavily into that. Let me just get my crib notes up so I can, because I can't remember all this off the top of my head. Here we go. It's not so much that I can't remember, it's just that I need to make sure I cover everything that I said I was going to cover to myself. Okay, so we're going to look at 2D truss frames. Let's go over here. Okay, we're looking at two-dimensional structures because they help us understand higher order problems. Okay, we've already shown that through looking at shear center, that helps us understand the concept of elastic axis, which is a 3D problem, by looking at 2D structures. We're going to look at 2D truss frames because they help us understand or utilize these methods. So truss frames are composed of 2 force members, and those force members are capable of only taking forces along their principal axis. They are composed of 2 force members which are situated between nodes or joints. and these are connected to a rigid support, or they are connected to the ground or a fixed frame of reference via supports. So we're going to look at these three things: two force members, nodes and joints, nodes or joints, same thing. Those two are always going to mean the same thing in this part of the module, okay? And we're looking at the two different supports. So it's probably easiest to describe these first, nodes and joints. So these are, when I draw my diagrams, these are circles, sometimes filled, sometimes not, depends how spicy I'm feeling that day. And these normally have Latin symbols describing which one they are, or Latin characters describing which part they are. So this would be node A, this would be node B. Two force member is just a part that is connecting them. Straight line connecting them, okay? So this would be member A, B. It connects node A or joint A to node B or joint B. Okay, and we call it a two-force member because it can only take X and Y, it can only take forces along this central axis, which is along its principal axis. So I've put here, member AB can only transfer forces along the principal axis, okay? So the force that would be present in this member, I'll give the symbol, lowercase f and AB, okay? That is the force present in this member. Now sign conventions here, I don't particularly care what your sign convention is, as long as you are consistent. What do I mean by sign convention? Well, we know that because this is a two-force member that's capable of transmitting forces just along here, it means that this member can either be in tension or in compression. We can consider tension pulls A and B closer together. And compression pushes A and B apart. Okay, so pulls A and B together, and compression pushes A and B apart. And I said sign convention here. What do I mean by that? Well, you pick whether a positive number means tension or whether a positive number means compression. I tend to use a positive number, so if I have a positive force FAB, that would give me tension, and if I have a negative number, that gives me compression, okay? But choose what your sign convention is going to be. As long as you're consistent within a single problem and you've said what it is, then that's fine. So pick one at the start of a problem. And stick to it. And then if you were asked, for example, to find, so let's say I've gone through an example, say I chose positive forces to indicate tension. And using the methodology that you all know from 202, but we're going to revise and go through, you did a free body diagram, you did a method of joints, you found that member FCD was equal to minus 13.1 kilonewtons. You've got that number. I would put after this, that is therefore in compression. Okay? Happy. Okay, this just means that when I see your answers at the end of it, I don't necessarily need to look at what your sign convention was at the beginning. You can just list this here. And if you, similarly, if you found FDE was equal to 1.1 kilonewtons, this would be in tension, for example. Okay, or you put a C or a T. Okay, this is just what those mean. And again, if you'd gone the other way around, if you'd chosen positive to mean compression, because that's the way you want to choose it, these two would then be the other way around. Okay, so that's what I mean by two force members, and that's what I mean by joints and nodes, and then supports are just the way that a structure is connected to a rigid support. So we tend to draw a rigid support as something that's like this, either a floor or can sometimes be connected to a wall, for example. So our supports can either be built in, like that, or we can put roller supports, and there's a myriad of ways we can write these. But let's say we've got this one here, this is built in. Now these two supports do two different things. A built-in support is there to stop lateral and vertical movement. So if I put an axis system on here, Y and X, then I have two reactions from this support. So let's say this is A and B, then there would be two reactions for this one. I'd have FAY and FAX. Okay, I've drawn these just outside of the actual diagram itself, but these would be working and applied at joint A itself. One that's on a roller has freedom to move left and right laterally on here, so this would just have, it would just have FBY in this sense. Okay, and then these are the forces that you would solve for using a free body diagram. You'd solve for these by looking at the equilibrium condition for the externally applied forces. So you've got sum of forces in the X is equal to 0, sum of forces in the Y is equal to 0, and your moments are equal to 0. So that's how we can solve for three external forces. Okay, so that is a good overview of, have I gone through everything here? No, let's go through this a bit further, okay? So I'm looking at, this is why I write my crib notes. Not that I've forgotten theory, I just forget what I'm supposed to be telling you guys. Okay, so we're not going to, like I say, we're not going to look at doing free body diagrams or the method of joints today, but we're looking at the things that surround doing pin jointed trusses. So why do we do all this stuff? Okay, so, well, we do them because they help us to understand structural problems and because truss structures are useful, that we actually use them. But these problems that you guys are going to be doing in this course, the aim in all of these problems, one way or another, is going to be to solve for an external deformation or to look for the force in an internal node. The force in an internal member. And in order to do that in these structures, we're going to have to solve for all the internal forces due to an externally applied load. Okay, so the reason why we do this, first of which I said, is because it helps us determine structural deformations, as we're going to show using work energy methods. The second of these is because it helps us determine member sizing. So say, for example, that we have got a truss structure that's got a built-in. In fact, let's say it's got two built-ins, and you have used the force method to work out all of the external forces on this structure due to the applied force P here. Let's say we've got A, B and C. So you've solved this problem, you've worked out all of those internal forces within the structure. So let's say you have determined F, A, B in this structure. So a couple of things are going to help us determine how big does how big does member AB need to be? Well, we know its length because we're given that in the problem. What we can determine is what its cross-sectional area needs to be. Okay, so once we solve for all of those internal forces, which hopefully again is just revision, we can remember our constitutive relationships, which is Hooke's law. So we can remember that axial stress is equal to modulus of elasticity multiplied by axial strain. Okay, sigma is equal to E epsilon. Okay, I used to confuse these Greek characters when I was an undergrad, so I'm just reminding you of those. E is Young's modulus. I don't need to write that down there. Okay, so stress is equal to force over cross-sectional area, and the strain is equal to change in length divided by its original length. So it's this is non-dimensional. This has units of newtons per square meter or pascals. So this one here helps us determine, for example, the maximum size. So once we've worked out FAB, that's this bit here. So you might find, for example, you know the yield stress of your material that's being used to build member FAB. And if you find that you've got a maximum yield stress, you need to change A such that for the applied force, you never exceed that. Okay? There we go. So that could be the sort of problem you could be asked in this assignment, using theory from, doing the method of joints, free body diagram, all of those things, everything. The end answer you might need to get is A here. We can also use this to solve for the external length by, let's substitute both of these into here. So this then becomes force divided by A is equal to Young's modulus multiplied by change in length on L. So we can then solve for delta L is equal to force multiplied by length divided by Young's modulus multiplied by area. And my camera has frozen. Still recording, thankfully. This camera is really buggering about today. Let's try this again. I think the writing stopped, which is good. So here we go, we're back. Need to get this looked at today. We're going to use this a lot. We're going to use this in all of the work energy methods, all of the methods. And my screen has stopped working. You can still hear me, which is good. So I need to put some. This hasn't finished. Let's see if this. I got rid of me, so that did that. Let's. I think part of the problem is that I'm capturing, because of the way that it's easy to capture, I use HDMI out from my iPad and then I have to use an HDMI box, which gets really warm. So I might have to start putting an ice pack underneath that. But where we are here, this gives us the change in length of a member is equal to the force going through it. So that F would be this FAB in this case, multiplied by its length. So that's just how long the member is, divided by its Young's modulus, or modulus of elasticity, multiplied by its cross-sectional area. So we're going to use this a lot in this course, okay? So we've got that, that's where we're going with this. This problem up here, for example, at the moment, using just the method of joints and a free body diagram, you couldn't solve this, and that's because of its static determinacy. So let's do a bit of a revision on what those things are. Yeah, let's go over here. So what is static determinacy? Or more interestingly, what is static indeterminacy? So this enables us to work out whether for a given structure the equilibrium equations are enough to solve the internal forces and reactions on a structure. So this concept tells us whether we have enough information to solve a problem or not. Okay, so the equilibrium equations we've got on the entire structure, sum of forces in both directions has to be equal to the sum of moments, which is 0. So this gives us 3 pieces of information that help us solve the entire structure. Okay, and then for each member, we've just got these first two. The sum of forces in the x and the y direction has to be equal to 0. Because each node isn't subject to a member, because it's a point load only, so it's a point where forces are applied directly into it. So it can't have a member, so it can't have a moment. So the equation that we use to determine if something is statically determinate, you say it is statically if the number of members is less than or equal to 2 times the number of joints or nodes minus the number of reactions. Okay, I'm using the, bloody hell. I'm going to have to do some playing around with my computer today to try and make this work better. It's been working the whole time through. I'll try and sort this out today. I don't know what's going wrong. If this is true, our structure is statically determinate. If this is not true, if m is greater than the right-hand side, then we are statically indeterminate. Okay, and then the degree to which the structure is indeterminate is given by its well-entitled degree of indeterminacy. Okay, so that is therefore dOI is equal to m minus 2j plus r. And for our purposes in this problem, we're going to be looking at degrees of indeterminacy of 1 mainly. Okay, either going to be 0 or 1, and if it's just 1, we can use the force method to solve for the external redundant support or the external redundant reaction. Sorry, forget what I just said. We're going to use this to determine the external redundant reaction or an internal redundant force. Okay, so how do we know which is which? Well, it depends whether the problem is externally or internally indeterminate. So problems may be internally or externally okay. It's externally indeterminate is the easiest one to actually recognize. One of the problems that I just showed you was actually externally indeterminate. So if we have a problem where we've got two built-in supports and let's just say we've got a suitable number of members and nodes between them, then you should be able to see immediately that if I put a frame of reference on here, which we should always do, then I've got two vertical reactions from these two built-ins and two horizontal reactions. So I've got four unknowns. So if I did my free body diagram, which you guys should be happy with doing, but I'll do a quick revision on tomorrow, four reactions externally indeterminate. And the reason for that is we've only got three equations to determine what these reactions are. That is, sum of forces in x, sum of forces in y, and the sum of moments has to be equal to 0. So we can't solve this using just the equilibrium equations. We would need to use the force method. Okay, so if a problem isn't externally indeterminate, but it still has a degree of indeterminacy of 1, for example, we could be looking at a problem like this. So let's say okay, problem like this. I've got one built-in and one roller support. So I've got, again, I'm just doing a real sketch here. This isn't good working. I'm just trying to go through theory rather than, theory of what determinacy is, not going through and solving this problem. So I've got three reactions here. Okay, so I've got R is equal to 3. Let's count joints. I've got 1, 2, 3, 4. Okay, this is not joined in the middle. We could join it in the middle, it would just become slightly more complicated to count the number of members. And then the number of members is going to be, well, it's 1, 2, 3, 4, 5, 6. So the degree of indeterminacy of this is m minus 2j plus r. So it's going to be 6 minus 8 plus 3 is equal to 1. Okay. And because it's equal to 1, that tells us that we've got a degree of indeterminacy of 1, which means we have a redundant internal member. One of these members is not required to maintain static equilibrium at all of these joints. Okay, so from having done these problems 1,000 times, I can see that it's either one of these internal members, the cross bracing. Okay, it'll become clear when we go through these how we get rid of them and how we understand which is which. But here we have an internal redundant member. Which means we could take one out and this structure, if every member was strong enough, would stay together. This one here has an external redundant support. Okay, and the external redundant support, it just means that this structure has got one too many supports on there. It's not necessarily means it's been over-designed, it's nothing regarding that. It just means that there is a support force that is not required to maintain static equilibrium, but can help determine, say, a certain distribution of internal forces. So the way that we're going to determine the forces either the external redundant support or the force in the internal redundant member, we're going to use the force method. And we're going to hopefully, I'll go through a full description of this next week, but I can give you a bit of an overview now because I think I said Wednesday here. So the force method, I said we'll go through on Wednesday. I'm going to briefly describe this, but we'll go through it properly, which is set, let's list this as a bunch of things, set redundant force equal to 0. Look at displacement without the force. Okay, so we set the redundant, say the external support, to 0, and we look at how much the structure would be displaced without it. We'll call this big delta. We then set redundant force equal to 1, just make it equal to 1 Newton, okay? And then we look at how much the structure moves in the other direction. And we call this little delta, okay? And what we'll show is that the redundant force, which we'll just call F, is equal to, we'll say it's equal to delta divided by delta, okay? So we're going to get this. This is the force method. I am fairly certain you guys have gone through this before. We're going to be doing this repeatedly in this module. I'll go through a full example, but what's different is we're going to use WorkEnergy methods to work out both of these displacements, just making the whole thing a lot easier for us. So this has been a big overview of lots of things. Let's just look right back to the beginning. Spoke about, so we're starting a new module. Spoke about last module. You've got homework to do, so hopefully everything's golden there. We spoke about truss structures and why we're using them, and I then gave an overview of what WorkEnergy methods are and what we're going to cover. Now I will give full lectures on these. I just want you guys to have a top level sort of think about what these things are. Okay, I told you the things that you guys should have remembered, and then you probably panicked about the things that you've forgotten, but we'll go through them tomorrow. We're going to go through these things. So we did this, we spoke about truss frames and determinacy, which should have been revision. That was all the yellow stuff. Excuse me, free body diagrams and the method of joints. These are revision. Okay, so I'm going to go through, and what I'm going to do tomorrow is I'm going to do some examples. And what I'm going to focus on is doing the theory, going through it. That's hopefully the revision. What should be new is doing some of this computationally. Okay, which means using Python, and I'll be doing examples for that. So we do all the equations, work it out, and then do it computationally. The reason for that is you'll see that using the force method, which should not be new to you, we've got to analyze the system with no force there and determine a displacement. That's a lot of calculation, and in order to do that, using WorkEnergy methods and the principle of virtual displacements, we actually have to solve the free body diagram once there, I think. Method of joints certainly twice just to get to this point. And here we've got to do the free body diagram again. And then here we've got to do the free body diagram and the method of joints, I think, twice again. So overall, we're doing this about 5 times to determine this bit that we care about. And once we've got this redundant support, we then have to do free body diagram, method of joints again to get everything. Okay, so 5 to 7 times we're going to have to do those same systems of equations over and over and over again. And anything I have to do more than once, I write a script to do. Okay, so we're going to go through that, and I'm going to put this heavy focus on doing things computationally, because I think it will help you guys become better engineers. Okay, so here's an overview of Module 2, a lot of stuff, and we are focusing heavily on the force method. Okay, so I hope that's been interesting, insightful, not too daunting. If there are questions, you know where to find me, and I look forward to seeing you all in the review on Wednesday. Take care, guys.